Imagine if every car could see the world the way pilots see an AR hood, which is rich, intuitive, and add a layer of safety. Good evening, we are Group 13, and today we are introducing Einstein Vision, an onboard visualization layer that turns a single forward-facing camera into a co-pilot you can trust.
In order to visualize the surroundings, we use state-of-the-art detection models. In order to calculate the depth values of the surrounding, we use Marigold. Marigold is a diffusion model and associated fine-tuning protocol for monocular depth estimation. We ran it on our custom dataset, which gave us results like this. Even though it was good, it sometimes fails in cases of occlusion. Now, once we have a depth map, we need to detect the objects in our surrounding, for which we use Meta AI's DEDIC. We can spot a huge range of road scene elements without task-specific retraining. DEDIC usually tags all passenger vehicles as simply car. When we make it tell sedans, SUVs, and pickup trucks apart, the differences are too small, so the predictions get noisy and produce more false positives.
Now, after detecting all the objects, we need to get the orientation of the vehicles, for which we use YOLO 3D. We ran YOLO 3D on each frame. It outputs a tight 3D bounding box, for which we extract the car's yaw. The front face of the bounding box gives us a usable heading. The orientation values were not accurate, but after applying some limits on the yaw values, we got the correct orientation of the cars. In order to detect the types of lanes and signs on the road, we use mask RCNN model. A custom mask RCNN takes the raw frame and segments the pixel accurate mask for each and every road markings. The model isn't just finding lines, it labels each class as solid center lines, dotted lane dividers, curbside edge lines, and direction arrows. Although model had some great results, but it had some false positives in the case of divider lines or in the case of markings with a fainted paint. Now coming down to human detection and pose estimation, we used OSX to detect accurate pose of human. It's a one-stage whole-body mesh network. OSX predicts a full mesh in a single forward pass, which gives us the exact pose of the person. It also holds up under night lighting, but if someone is far away or half occluded, the limbs can fold in, but we still would get a accurate pose. Now, in order to detect if the vehicle is moving or parked, we used optical flow for classification motion. There is an edge case when a driving vehicle is straight towards the camera, its apparent motion is small, so we occasionally miss it.
Now coming to visualization board. In order to give a good experience to the users, we used a third-person view. So first we need to add our own car. Now we need to project the lanes we detected. And we also did the color segmentation on the lanes, as each lane has its own significance. Now let's go and add the traffic lights with the directions. In the end, we'll add all the vehicles alongside their directions of motion, which is represented with the arrows. And now, when we play the scene, we can visualize our whole ride on the visualization board. Here we are also detecting the brake lights and representing them in the visboard. There are some failure cases, like we can see in the bottom corner. Model do get confused with their vehicle subclasses. We are also projecting the humans on the sidewalk with their accurate poses. Smaller vehicles such as bicycles, speed limits, and speed humps, which help in enhancing the user's comfort and experience.